Good afternoon. This is Schweitzer. We're doing a little video here on projectile motion, um, graphing representing this material in a specific way. All right, so let's grab this here and see what they're talking about. A rock is thrown horizontally with speed v at the top of a cliff at height h, as shown to the right. Okay, we've seen this already. All right, so we're going to sketch this out graphically. Part A, sketch the following graphs of motion of the rock on the axis provided below the diagram to the right. Okay, so sketch the motion of the rock on the axes provided below the right. Okay, so let's do that here. Vertical, horizontal. Okay, we're doing, looks like we have acceleration on one side and time on the other. Okay, so this is important. Okay, so a couple things here. One, we should note that gravity only pulls down. Okay, so does not act at all in any direction other than vertical. So that being said, in the vertical position, you could mark out 0 here. However you want to gauge this, 2, 4, 6, 8, 10, or if you want to go like that, it would be -10. So vertical, it would just always be the same. Let's say that guy here is -10. And then here in the horizontal would be just like nothing. Okay. All right, and velocity. Okay, so in the horizontal position, we're throwing it at velocity v off this thing horizontally. So the velocity, there's no acceleration, but the velocity is constant in this direction, so it's positive. Whatever v happens to be, I'm going to put like this. It's just going to be, constantly the same all the time. Um, Vertical starts out at 0, okay, and it in an exponential manner, it just continues to get faster and faster and faster. We're not looking to quantify this a whole lot, but we're just going to kind of go like that. Okay. It's velocity. Position y, position x. Okay, so this, keep in mind that the slope of this line, okay, is equal to the x over the y, which is the rise over the run, which is going to be velocity, which is this guy. So since I have a constant velocity horizontal, I'm starting from the 0 point. I would note that we're going to hold a flat line here. Okay. Yeah. And then here you should note vertical that I'm gaining speed, accelerating. So I'm starting out slow and I am speeding up. So I have a negative velocity and a negative acceleration. I have to keep that in mind. So I need to go think about this. I need to start flat and need to get more vertical. That would be a situation of a negative velocity with a negative acceleration. It's 0 here, so I'm below the line. So it's going to look something like that. Okay. Great exercise. All right, we just did the first part here. A second rock is thrown at an angle above the horizontal at same speed. Okay. Now keep in mind, same speed. Okay. Some angle here. So now, if I have angle, if I'm throwing it at this guy with velocity v, then I'm going to get a smaller portion of that velocity is x, and a smaller portion of velocity is now y. Okay, velocity y. So I'm not getting the same, I have a smaller v, okay, vx, and I have a small up v. All right, so at the same speed v at the same height h as the rock in part A. On the same set of axes as part A, sketch the graphs for the second rock. If the graphs for part B are different than the part A, use a different color to show the lines. Okay, let's grab a different color. Okay, so all right, so horizontally, I mentioned that because this component on a triangle is always smaller than the hypotenuse. This guy here, oh, acceleration-wise. Okay, so acceleration-wise, okay, still no acceleration. Same. Gravity hasn't changed. Same. All right. All right. Horizontal velocity, less. I don't know what the angle was, so I'm just going to go like right here, less, because part of the velocity is going up. All right, so vertical. Okay, this definitely is going to be different because we're actually throwing it up. So some of the velocity it's going to go up. It has a positive velocity and a negative acceleration. Okay, so what does that look like for vertical velocity? So it's going to have a positive velocity, and then it's going to go up. It's going to then stop. Okay, so this thing is going to go up in the air. It's going to stop. Velocity equals 0, and then it's going to start coming back down. Okay, and at this is the cliff here. Okay, so let's think about this. So here we have a positive velocity and we have a negative acceleration, which is gravity, so we're slowing down. Okay, our velocity is the maximum right here, and it just gets smaller and smaller and smaller. Now the slope of this graph is velocity divided by time, which change in velocity divided by time, which is acceleration. So notice that the acceleration in this situation is flat. It's constant. Okay, it's g, it's gravity. So my slope in this line should be flat. Okay, so in this situation, all right, I should probably have a line that's flat, and this line here also should be flat. Okay, yeah, right. So it has to be flat because the slope represents that of acceleration. Make a note of that. Okay. This line here should be -10 for gravity. Now this one starts out essentially a little faster and just goes like this. Okay. Starts out with a maximum velocity, which is going to be positive v, which would be the upward component of this triangle, vt, vy. This is where it reaches its maximum tip right here, and then it starts going negative and gets faster and faster, faster negative. Okay. Great. All right. All right. Now position. Okay. So position here, again, let's think about this thing, draw a picture of it again. Position wise, it goes up and it comes back down. Here's our cliff. And it's really going to show vertical is going to be this, start the same spot. It's going to go up, okay, and its slope, once again, is velocity. So it's going to go up, it's going to come to a stop. So just drag this out. It goes up, comes to a stop, and then it starts to accelerate down. It's going to likely mimic this same motion, which is the parabolic motion. There we go. Right. And then this one here, horizontal, well, it's horizontal, really it's going to be less and constant, like that. Okay. Any questions? All right. Okay. So notice that if this is the ground, vertically. This one will reach the same ground, but it would be a little bit in the air a little bit longer if we throw it up. Okay? Obviously, throwing a ball horizontally versus throwing a ball up at same velocity, it should be in the ground for the same in the air longer. Okay, so let's go to part C. If a second rock is thrown horizontally, did I do this? Yep, okay. If a second rock is thrown horizontally with a speed 2v, would the horizontal distance d be the between the bottom of the cliff and the place where the rock lands be larger, smaller, or the same? So horizontally, okay. And the answer, check a bird box, would be, so in this situation it would be larger, okay. All we're doing is throwing it off the cliff faster. We're in the air the same amount of time, it's just going faster, so it's going to land out farther. Okay. All right. Evidence. All right. The blank physical quantities for both rocks are the same. The time is the same. Okay. So the physical quantity. So what's the same? The height is the same. The acceleration is the same for both rocks. So therefore, the time it takes to fall is also the same. Since both rocks are in the air for the same amount of time, the rock given horizontal faster would be B goes farther. The second rock. Okay. All right. And that is an excellent exercise. Thank you.